Um, so yeah, today we're gonna talk about the postulates of quantum mechanics. We're gonna finally connect all this math to some physics, and we started on it a little bit already, but let's just go through it again. Postulates of quantum mechanics. This is like, if you really understand these and all the Hilbert space stuff that we talked about, then that's basically all of quantum mechanics. Everything else is just sort of details and examples. So the first postulate is any system is fully specified by a vector in a Hilbert space. And we saw last time that this is true up, it's up to a phase. So if you multiply the vector by some complex phase, then that doesn't change any of the physics. So you could take e to the I alpha, multiply it by phi, and that's still the same state. That's still the full specification of the system. So some people say that that a physical state of a system, the full specification of a state, is array in the Hilbert space. Array meaning a vector times any of these directional phases. As the phase gives you, right, a direction in the complex plane. So it up to this phase, that's a full specification of the state of the system. So this is sometimes called array in the Hilbert space. It's not a vector because a vector has a unique phase, but it's any vector, up to a phase. Sometimes it's called array. For those of you who are interested in mathematics, I guess. And the other thing is, in order for the postulates to make sense, you must have that the states are normalized to 1. And this is because of the fact that these are going to be connected up to probabilities, which comes in postulate 2. The probability of finding a system in state, say, some other chi that's in the Hilbert space, right, is p chi. It's going to be the inner product between the state that the system is in and chi. So that's the Born rule. And obviously, the fact that this is the connection gives you this up to a phase and the normalization. Because if you're in a state, the probability of finding the system in that state is going to be 1. It has to be true. It's sort of by definition, by logical definition of what we mean by sort of probability. And postulate 3 is any physical property, and this is important because it's really anything we understand about a system, the position of something, the momentum, the energy, angular momentum, whatever. Any physical property is associated with a Hermitian operator A. And that's very important, and because then we know that A will have some eigen values, right? This is a spectral decomposition theorem that we talked about. Has some eigenvalues, an, and eigenvectors, n. And these guys will be the results of the measurements. Results, it's the possible results, right? Possible results of measuring that property. Put A in quotes. So any physical property, right, has a Hermitian operator associated with it. So then we know automatically from our understanding of Hilbert spaces and spectral decomposition theorem that A is going to have a set of real eigenvalues and some eigenvectors which form, these are special, right? They form a basis for your Hilbert space. And so any physical property has this Hermitian operator associated with it, and that automatically tells you the set of possible results of measuring that particular property. So quantum mechanics, like ingrained within it, is the idea that there's no such thing as having a definite measurement outcome, in a sense that the possibilities for measuring, for finding a particular property of the system is associated with an eigenvalue of the Hermitian operator associated with that measurement. Now, of course, it could happen that maybe your system's already in one of these eigenstates, right? And if it's in one of these eigenstates, then you will always measure the corresponding eigenvalue for that property. So then you can have a sort of idea of a definite property of the system. But in general, for any given state, that's not going to be true. So the probability of observing a particular outcome of this measurement is just going to be, the dot product between the associated eigenvector of that eigenvalue. So this is the probability of observing an for that particular property of the system. So if that's the case, then there's lots of things we could do. We could, for instance, calculate like what happens if you take a bunch of these systems and you measure that same property over and over again, right? You could have the idea of an average value for your physical property, which would just be A, we put a little phi because that's the state of the system that we're preparing the system in. So you prepare a system in some state, you fully specify it, according to postulate 1, and then you can measure. If you take a bunch of copies of the system, or you keep preparing it and measuring the property, you can calculate the average, and the average has to be, of course, the sum over all the possible outcomes, probability of finding that outcome times the eigenvalue there. And this is by definition of what an average means, right? This is an average. What's an average? It's the probability times the value, and you sum over all the different possibilities for the value. And what is this? We can now use our Dirac notation to expand this out, right? We can start writing things in a sort of quote unquote clever way. We could rewrite the probability as the following, and then we could absorb this an, right? We could absorb it into here if we want by introducing the operator back. So you got n phi, and then I'll stick the a in here because it's n is the eigenvector associated with the eigenvalue. And now this is nice. We can switch these around, and what do we get? We get phi a n and phi, and look at that. We again find the magical completeness, relationship that, we're summing over a bunch of projectors onto the basis. So this is that just comes out as a one, an identity operator. And we get the expectation value. So this is really the heart of quantum mechanics. And in some sense, you might wonder, like, where does a Hilbert space even come from? Well, and one way to think about it is, say you're interested in measuring something about a system or knowing something about a system. The fundamental thing is, of course, it's the operator associated with that property. And the operator automatically gives you a set of eigenvectors and eigenvalues. And your Hilbert space is whatever space is just spanned by those eigenvectors. And this idea of the completeness relation is a crucial one. It says that these projectors onto these all correspond to particular measurement outcomes. They give you a Hilbert space. So one way to think about quantum mechanics is, you say you want to measure something about a system, you identify the Hermitian operator associated with that property, be it position or spin. Spin is something, or polarization. That's something we'll look at. We'll look at spin and polarization pretty soon here. And each of those measurements that you make has a set of possible outcomes, right? You can do the experiment. You could measure the spin, and you'll find some set of outcomes. For spin, you'll find that there's, for instance, for a spin 1/2 particle, if you measure the spin along some direction, you'll find one of two possible values, spin up along the direction you're measuring, or spin down. And that automatically, those are your measurement outcomes. That automatically tells you what your Hilbert space is. It's, it's the Hilbert space spanned by the two eigenvectors associated with spin up and spin down. And so you get a two-dimensional Hilbert space. And in general, however many, so number of measurement outcomes, right? Possible measurement outcomes is going to be the dimension of the Hilbert space, typically. So like for spin 1/2, you can measure spin up or down, then, there's two different measurement outcomes. And so you get two different, eigenvectors. And so they span a two-dimensional Hilbert space. Any questions about that? It's pretty crucial, these three.
About the expectation value.
Yeah.
Here, phi is normalized, right?
Yes, that's part of the postulates are all kind of connected to each other. Yeah, so phi is normalized.
We can also compute expectation values on phi is not normalized, right?
You could, but then it wouldn't correspond to the average of a physical property of a system.
Okay.
Yeah.
Okay.
Okay, so any more questions? These are really pretty important. This one's called the Born rule. And it's important to note that these are, you have to perform multiple experiments to calculate the average. This isn't something that you measure once. This is like you set up the system and then you measure some property of it, the position of something, the spin of something. And if you measure that property over and over again, you'll get a set of possible values for, that property. And each one will occur with some probability. And only if you repeat the experiment a bunch will you then get an average value for that measurement outcome. You have to do it over and over again because you have to sample the probabilities. And so that kind of brings me to, this is a little bit of an aside, but since quantum mechanics, the physics of it is, deeply connected to probability, we should mention at least what probability is. So the probability, and this was sort of worked out, the formal sort of definition of it was worked out by Kolmogorov in 1933. So you see, it's kind of contemporary with quantum mechanics. Ideas about probability were formalized around the same time. So it's probably not a coincidence. All these things were sort of developed simultaneously. So probability requires a space of events. This is like all the things that can happen. And for us, it's going to be the eigenstates or values of some property that we're measuring, which is described by a Hermitian operator. And there's a measurement, PE, which tells us this is going to be the probability of some event E that lives in this space of possible events. So this is like the probability of observing a particular outcome of some measurement. And there's just some rules that it has to satisfy. The probability has to be greater than or equal to 0 for all events in your space. It also has to, something has to happen. So the probability, let's see, what's a good, let's see, it's a good.
Would it just be like the sum of probabilities of E sub I over all your possibilities equals 1? Is that what this is getting at?
Not so. There's a better notation for it. Yeah, that's the right idea, but we have to be careful because so we have to be careful because there will be a distinction between, right? So these events, right? If we have, say, a continuous part of the spectrum, say we're measuring something like position, right? Then, yeah, so say we're measuring something like position, P of X. Yes, in principle, if we sum over all the different, possibilities for observing a particular position X, then this has to be equal to 1. But X is typically continuous, which is what we'll spend a lot of time looking at later on. So there's another notion here that you can have a probability density that you can integrate up over all the different positions, and that this integral is equal to 1. So I'm trying to think of a good, so I think let me think about it. So the technical mathematical thing is that you define a set of, this is like called the sample space. This is like the set of events that could happen. It's the set of possible events, like all of them. And since we know something must have happened, then the probability that any one of these things happened has to be equal to 1, and that's the more formal way of saying it. But it doesn't really come up. I was trying to make a good analogy, but I can't think of one right now. But this is the formal thing, that the probability of the whole sample space has to be equal to 1. And then the other thing is that if you have the probability of a union of events, say you have different possible events, and you ask what's the probability that either 1, 2, or 3, and so on happened. And if these are, as long as these are disjoint, meaning only one of them can happen, right? You can't have like both happening simultaneously, then this is just going to be the sum, up to however many events of the probability of the individual events. So, and then there's the last kind of, there's a last point which sometimes comes up when dealing with probabilities, is that if you want a probability of like figuring out some event, given, this means given that some other event happened, we call it F, or no, I would call it E bar maybe. This is the probability that you find event E, that you find outcome E, given that some other outcome happened for some other thing. It could be like some other measurement that you already did on the system, and you found some given outcome. Now you want to know the probability of finding another outcome. The probability of that, this is given by the probability that both events happened. This upside down thing is the intersection. This is the union. This is the intersection of the two sets of here. This is both happened. Divided by the probability that just the first thing happened. That's the other rule. Sometimes comes up in quantum mechanics also.
What is the is the line average over that E? What did you say the line was again?
No, this is event 1, if you want, and this is some other event.
Okay, but that line doesn't have any meaning over it.
It's just like another event. I don't know. We could have made it 1 and 2. Maybe that's better.
Oh, okay. Because I was just wondering what that. Because see, sometimes I know in my other class it does mean something different.
I don't. Yeah, I just wanted some notation for some other event happening.
Omega is an F?
So the way to think about it is you could have, this is where it gets a little bit, technical. So omega is a set of events. So it's a collection of events, and it's the set of all the possible events that could happen. And so, yeah, maybe if I figure out maybe a better way to, or maybe when it comes up again, I'll try to be a little bit more precise.
Okay.
But yeah, technically speaking, omega and F are different because F is a set of events and omega is a set of so it's a sample space. It's the way in which we sort of sample the events. So this is like a set of outcomes, and then this is, it's a little bit subtle. Generally speaking, omega is not equal to F mathematically, but maybe it's best to think about it as if they're the same thing for now.
But is it but is it a subset of F, or is it bigger than F? I guess that's which space is in what? Or is there a relationship between the two? When you say P of omega is equal to 1, is that like someone else was previously saying that is that the total set of all events, which is E1, E2, E3 till infinity. I don't know. So I guess my question really is, what is the relationship between omega E and F?
Well, okay, so let me do maybe heads and tails or something. Say you have a coin that's either heads or tails. Then F is, heads or tails. But the sample space is the different sets of coin flips we could have. And then that depends on, how we do the sampling. Say we could do like 3 coin flips in a row. And then omega could be something like, heads, 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 tails, heads, tails, 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 or something.
Okay.
And so on. So it's a little bit, it's a little bit subtle, I guess. So the sample space is how you do the sampling of your events, and you could do 3 coin flips in a row or something like that. And so this gives you, the whole set of outcomes that you could get from doing the sampling. F, though, it just gives you the events themselves, like heads or tails. So that's roughly the difference.
Yeah, that's pretty good, actually. That's good.
Okay. All right. Good. Maybe I'll do something a little more formal later, but this is really outside of the scope of things that we're talking about. I just want you to know that there's a formal development of probability that is connected up to all of quantum mechanics that sometimes people don't quite appreciate that that's what that's what's going on behind a lot of these things. Because, I mean, look at these postulates. The only physics here is here, right? It's right here. It's in the Born rule. That's all the physics in quantum mechanics is embodied in the Born rule, and well, that's kind of a problem because we don't really in physics talk about probability very often in a formal way. But all of quantum mechanics is built on probabilities, so it's a little bit strange if you think about it. So maybe we'll develop it some more later, but just something to keep in mind. More questions?
Yeah, so the probability that you wrote at the end, can you go back to that part?
Sure. Yeah, this one?
Yeah, the last one.
Yeah, this is special. This is technically outside of the axioms that Kolmogorov put down. This is something that lets you talk about events that can happen at the same time, or it can be, measurements that you can perform on a single system. This is like the probability of measuring a position given that you measured something else, right?
So is it, so it's the probability of happening both events at the same time?
Yeah, it's the probability that both happened divided by the probability that this event 2 happened.
No, the one on the left side.
No, so this means this is the probability E1 given that you assume that E2 happened.
So this is conditional probability, right? So
Yes.
E2 happens and then what? Okay. Okay. Yeah, I was just confused with that, the vertical bar notation. Okay.
And what we mean by that is it's the probability that both happened divided by the probability that just E2 happened. And, you can use this to derive the Bayes rule, and, maybe we'll talk about that later. There's lots of fun paradoxes with that. But anyway, it's just important to keep in mind that probability plays an important role in all this, and it's formalized. There's a set of axioms for it, and those axioms are kind of embedded in here, right? This is normalization of probability. And this whole thing is this idea that, PE has to be greater or equal to 0, this kind of thing. This is essentially P omega is equal to 1. there's a relationship, a direct relationship between the axioms of quantum mechanics and kind of formal notions of probability. Okay, more questions about that before we sort of move on to consequences of 3, I guess, or some more postulates? All right, I'm going to clear this. Okay, so in 3, you can think about 3b. It's not a separate postulate necessarily, but we think about, say we measured some outcome. Say we found an, right? Well, what do we do with our state, right? Well, like, what do we do now after we've measured that? Well, we have to update our information about the system, right? We found something out, so the state, our informational state about the system changes. I mean, often when you measure something, it's destructive, like the particle hits a screen, or like, you know, a click is detected in a photon, you know, one of those photomultiplier tubes. So typically, the, you know, phi maybe gets destroyed, and you don't even worry about it. But in principle, you could perform, you know, a non-destructive measurement, and I can put in here non-destructively. And if you non-destructively measure something about the system like that, well, then phi has to go to a new phi prime, which is just the projection onto the eigenvector associated with associated with that outcome. It's, you know, pretty, and you, of course, you have to maintain normalization, so you divide by the normalization. This ensures that your phi prime is also, you know, a physical state. And you can think about that as just being a projection operator acting on the state phi, you know, divided by the magnitude of, you know, the projected guy, and make sure everything is normalized. So that's where projections come in. The projection operators basically tell you how you update your system after a non-destructive measurement of some property. You project the system onto the associated eigenvector, and then you just normalize, and that's how you update the state. Okay, so let's do another sort of consequences, also kind of an aside, and talk about Heisenberg inequalities. See, once you have these postulates, everything just kind of follows through with it. And you might wonder, oh, well, what about the Schrodinger equation and all that? That actually also follows, as we'll see, from those 3 postulates already stated. The dynamics of a system is actually a logical kind of consequence of the postulates, as we'll see. So, okay, so what about Heisenberg inequalities? Those are kind of famous. So Heisenberg inequalities have to do with 2 different operators corresponding to measurements. So say you have 2 measurements, A and B, and then you can define a kind of fluctuation of any measurement away from its average value. It's kind of like the variance, if you want, and it's denoted by the following. It's like a variance, if you're familiar with probability. And what it is you take the average of A squared, you know, with respect to the state of your system, and you subtract off the average of A squared, right? These are different things. Here you're squaring the average, here you're squaring the operator and then taking the average. And that's, you can, do a little algebra. It's easy to show that this is just A minus the average of A, times the identity, squared averaged over phi. You can show that. You should work it out. Maybe I'll put it as a subpart on a homework. So this is really taking the average of what? It's the average of all the deviations of the measurement A away from the average value of A. So these are like the deviations of A away from the average value. And we're squaring those and averaging. So this is a precise number that you can get by averaging over many, many experiments, right? It's kind of like you can measure the average value of something that you get in an experiment, but you can also measure the average spread of the values around that average. You can measure the variance. If you do a bunch of experiments, right? You say you measure, a bunch of times, you get like a distribution where you get a bunch of, so this is number of events, right? And this is the A that you observe. So you might observe a bunch of A's at around the average value, right? So you have lots of numbers here. You do a little histogram. You can plot a histogram of all the different values you observe, right? And you'll get some distribution around the average. And so this, this is the average. And there will be some spread of this distribution, and that's captured by this delta phi A. It gives you the average spread of, the measurement outcomes that you find. And, and if it's a symmetric kind of thing, it'll be some distribution around the average. Okay, so that's great. But, and then of course, you can also do the same thing for B. So you have these two fluctuations, and now you can think about, let's think about the commutator, A comma B. The commutator is interesting. If we take its Hermitian conjugate, what's that? You get AB minus BA. Hermitian conjugate, that is, what is it? Well, you do this dagger, you do B dagger, A dagger, minus A dagger, B dagger. And so this becomes, right, this becomes the commutator between B dagger and A dagger now. But these are Hermitian, so this is just BA, which is also minus AB. So you see, if you have a commutator between two Hermitian operators, it's anti-Hermitian. So we can write AB as its own operator, where C is Hermitian, multiplied by I. That guarantees this property that, when you take the Hermitian conjugate, you pick up a minus sign because of the little I. Okay. So now what? Now let's look at the following. So we're going to try to connect basically the fluctuation in A, the commutator between A and B, and the fluctuations in B, of course, So we're gonna try to see if we can connect up, 1, 2, and 3 into some kind of inequality, which will be the general Heisenberg inequality. Like the position and momentum, uncertainty, relation, all those things. They're just particular examples of this very general rule that just comes from combination of probability, understanding, variance, and basically the idea that, measurements correspond to operators which may not commute. They might You might not be able to perform the measurements simultaneously and get simultaneous. Remember what this means. If these guys don't commute, right? If A and B don't commute, that means you can't find simultaneous eigenvectors of A and B. You can't have definite measurement outcomes of both properties, right? That's what, if C is non-zero. So if C is not equal to 0, A and B do not have simultaneous measurement outcomes, right? They're incompatible. Okay, but let's just go through the algebra now. So let's look at this combination of, so let's define A0 as A minus and B0. This is these deviations. It's just to make the notation a little bit more compact. It's these deviations. We'll denote them with a little 0. Let's look at the following. Let's look at the magnitude of A naught plus I lambda B naught acting on some vector in your, the vector corresponding to your system state. Let's look at the magnitude of that squared, right? So what's this thing? Well, there's going to be a phi A naught squared phi piece. That's one of the terms. There's going to be a magnitude of lambda squared. And again, this is just some complex number. Remember, just like we did when we were proving, well, various things like Cauchy-Schwarz and things like that. It's sometimes to get like a connection between different pieces, like these 1, 2, 3 things, you just pick a linear combination with them, and then you use some property like that the magnitude of a vector in your Hilbert space is greater than or equal to 0, which is what we're doing here. We're taking these two operators acting on a state, and we know that the magnitude squared has to be greater than or equal to 0, because this just gives me another, this is just another vector in your Hilbert space, right? This is also an element in your Hilbert space. That's how it all fits together. When you have a measurement operator, right, if it acts on your state, that is also a state in your Hilbert space. So it has all the same properties as any state in your Hilbert space. So we can use these things to prove various properties of measurements. Okay, so we got this. We've got this guy, right? It's just from squaring. And then you have the cross terms. Well, there's the I lambda piece, which is phi, and then it's A naught, B naught, phi. And then you've got the other one where you have the antilinearity property. Oops. And then you come in with a minus minus I lambda star, right, of phi, and then this is now B naught, A naught, phi, and all of that has to be greater than or equal to 0. So, okay. So far, so good. All right. So now we can, if we suppose lambda is real, which we can do because it's some arbitrary parameter. So if we suppose it's real, then of course lambda and lambda star are the same thing. And these combine right into the commutator. So what we find is that phi a naught squared phi plus lambda squared phi b naught squared phi, and then this becomes plus I lambda phi, and then this just becomes the commutator between a naught and b naught phi, and that's greater than or equal to 0. Now, why is that good? That's good because look at this I and this thing right here. If we go back, if we go back here, right here, well, the commutator between a naught and b naught, since these are just the identity, we're just subtracting off a constant, just an identity matrix. An identity matrix commutes with everything. Then the commutator between a naught and b naught must be the same as the commutator between a and b. And if I tack on a little I here, like this, then this just becomes minus c. All right. So, right, so then we get that this becomes minus lambda phi c phi. And that's very good because lambda now, you see, is comes in here as a quadratic form, right? There's a lambda here. So, and what are these guys? These guys, these are just the variances, right? This is a naught squared average is just the fluctuation, right? This is a naught squared right here, this whole thing. All right, so this whole thing is, going back here, is delta phi of a squared plus lambda squared. Since it's real, I can drop the magnitude. Delta phi of b squared minus lambda, and we just call this c phi, right? That's greater than or equal to 0. And what it means is that this whole thing, if we calculate these things, right, in an experiment, these are just some numbers. What it's saying is that if we are to plot this, and this has to be true for any, this inequality is true for any lambda. And what that means is if I were to draw this equation, right? If I were to plot this quantity right here, let's just call this x or something, plot x as a function of lambda. Well, this is a quadratic in lambda, so it forms a parabola, right? So this quantity x has to form some kind of parabola. And what it's saying is for any value of lambda, this x can't go negative. So this parabola has to be pointing up, and its minimum can't go past down into the negative values, right? Well, hopefully that makes sense. So, x here is as a function of, it's some function of lambda, right? It's this entire quantity. It's this whole thing, the left-hand side. And this inequality means that, this thing for any lambda has to be greater than or equal to 0. So it has to, and since it's a quadratic form here, it means it makes a parabola of some kind. And the parabola has to be pointing up, and its minimum can't pass down below the lambda axis. It can't go negative. So that's actually enough to figure out a relationship between all of these numbers. In particular, so let me So if we call this, say we call this guy little a, and this guy little b, and then this guy is little c. Then we know, so a plus lambda squared b minus lambda c has to be greater than or equal to 0. You can actually find the minimum. You can find the minimum of that parabola. The minimum, right, has to occur at, you take a derivative of this side, right? This is your x of lambda, right? You do dx d lambda, right? So that gives you 2 lambda b minus c, right? That has to equal 0 at the minimum. So lambda star, you know, the value of the minimum, lambda star, has to be c divided by 2b. And now you can evaluate your x at the minimum, c over 2b. And what do you get? Well, you get a plus c over 2b squared times b, right? Minus c over 2b times c, so c squared. Okay, and this is equal to a, and let's see what happens. This becomes c squared over 4 minus c squared over 2, so this becomes minus c squared, right, over 4b. And it has to be greater than or equal to 0, because again, this minimum has to be off of the x-axis. It's gotta be off of there. And so this inequality only works if this is true. And we can rewrite that, of course. We can rewrite it as c squared over 4, right? Has to be less than or equal to ab. And if we go back to what that means, it means that in a particular, we can just take the square root of both of these if we want. Take both sides of the square root, that's allowed. You know, they're both positive things, which they are. So you get 1/2, right? And what was little c? That was just the expectation value of that commutator piece. Has to be less than or equal to. This provides a lower bound, right? A lower bound on the product of the fluctuations. This is the delta phi. So square root of a is just delta phi a, right? Times delta phi b. So if you have two non-commuting measurements, incompatible measurements, then their commutator defines the average of the measurement of that commutator. The commutator is itself something you can measure. That defines a lower bound for the fluctuations in the distribution. It's really an amazing thing. And all of these can be measured separately, right? You perform a bunch of B measurements, you get a little distribution of Bs. Perform a bunch of A measurements, get a distribution of As around the average. You compute these little fluctuations over many, many experiments, and lo and behold, when you multiply them together, those two uncertainties, or the two variances, they're bounded. The product is bounded by the average value of their commutator. So just from properties of Hermitian operators alone, right, we're able to derive a relationship between measurement outcomes, right? That the uncertainty, and it's really a subtle thing. It's not, people like to talk about uncertainty as if it has to do with like a single event or a single measurement or something of a system, but it's not really like that. It's a property of the probability distribution, right, of a bunch of measurement outcomes. It's the uncertainty in the, of the probability distribution that describes that system. And the way you get the probability distribution is you do a bunch of experiments over and over again. You see what the spread in the measurements is. And what you find is if you have two incompatible properties like position and momentum, the spread in the positions that you measure and the spread in the momenta that you measure are bounded. They're related to each other in the following way, that the product of the two standard deviations is always bigger than, it's bounded by their commutator. And we'll see that the commutator for position and momentum is, of course, going to be IH bar and so on. So this will be related to, this is something typically quantum. This is, like H bar, something like that. But you see, it has nothing to do with position and momentum. It's just a fundamental property of operators and the postulates, right? All right, so hopefully that makes sense. Oh, and of course, if C equals 0, then this is a trivial thing. Obviously, a product of two positive numbers is going to be a positive number, so that doesn't tell you anything interesting.
Could you scroll up for a second?
Sure. And look at this, we derived it just from like normalization of a vector in Hilbert space and just like properties of operators. That's it. It's like it doesn't require much at all to show this, right? Like nothing, basically nothing. Just basically the fact that Hermitian operators, their commutator has to be anti-Hermitian. That's one thing. And then the other thing is just that vectors in Hilbert spaces are, have positive norm. That's it. Or, have non-negative magnitudes. Any questions? Really pretty deep thing. So any two measurements that are incompatible, or your system can't have definite outcomes for both simultaneously, any one of those, that means they don't commute, then all of a sudden you get a bound on the spread of the values that you find when you perform an experiment, measuring those two different properties. Pretty cool.
So say that two operators do not commute. That is, you cannot simultaneously get measurements of those two operators.
Yes.
That are with any certainty. Or
that's right. Because, sorry, say again.
Go ahead. The certainty is bounded by the half C that we just derived.
Yeah, well, I mean, the idea is that it just goes back to what we know from, our math. The math says that if they don't commute, you can't have mutual eigenstates, right? You can't construct things that you can't construct these states, right? They give you definite outcomes of both A and B. This is not like a thing that you can have.
Mm-hmm.
Nope, not allowed. Nope. Like if A and B are not equal to 0.
Okay.
Then you can't have that. So that's the sense in which I mean you can't have simultaneous. Any state of the system will not be in a definite state of both, right? It can be in a definite state of 1. It can be in an eigenvector of 1, but it won't be an eigenvector of the other one.
Okay.
Right. That's what we mean in quantum mechanics by like incompatible. It just goes back to just the property of Hermitian operators. Once you say that a measurement corresponds to a Hermitian operator, it gives you like a whole basically everything can be derived, from first principles from that, right?
Mhm.
You automatically know that you can't have a state of a system that's, has a definite value for that measurement and that one simultaneously. Then you automatically know, just from the property of a Hilbert space, that if you measure those two properties individually over, the same preparation of the system over and over again, then the spread in the values are related to each other. If the spread gets really big for one of them, if the spread gets very narrow for one of them, gets really small, right? If you get a really precise distribution for like position or something, and that variance, that standard deviation there gets really small,
Mhm.
then as a consequence of this general relationship, if one of these gets really small, then this one must get bigger to compensate in order to satisfy this bound, right?
Makes sense.
If they're
Right.
getting close to the bound.
Right. Okay.
So,
Yeah, that makes sense. That's good.
okay.
Thank
great.
you.
Sure. Yeah, so this is I want to linger on this, for a little bit. Any more questions?
I think I would like to know how you would. We have discussed this before. About have we discussed this in terms of like compatible observables? In that
Yeah.
case, I guess it doesn't really matter. Is that?
Well, two compatible observables would be ones in which, A comma B
Is equal to 0.
is equal to 0. And if they're compatible, all your inequality tells you is just that the spread of one times the spread of the other one is just greater than or equal to 0. This is always true anyway.
Right. Okay.
It's always true anyway because the spread is by definition, bigger than 0. It's like
Right.
product of two positive numbers.
Mm-hmm. Okay. Just making sure that I understand it.
Okay. All right. So, okay. Any more? Or we good? Good. All right. So this is a consequence, and all right, I'm going to clear this for now. And okay, we can talk about the fourth postulate, but the fourth postulate, and it has to do with the Schrodinger equation. Postulate 4 is, I don't know, it's not, yeah, it's a postulate, but you can actually just derive it like using pure thought, which is what I'll start now. I'll probably finish it next time and move on to examples of qubits. But postulate 4 is that, phi, your system state, evolves in time. According to the Schrodinger equation, which is IH bar, a derivative with respect to time, acting on your state, which now depends on time. And that's equal to your operator H. This is your Hamiltonian. It's the operator associated with measuring the energy, E measurement. And that's how it evolves. So it's first order equation, and it just tells you how to take any system at time t equals 0. This is your initial condition, right? If you don't do anything to the system, like you don't measure anything about it, you just let it evolve in time, then it'll evolve according to this differential equation where, it's IH bar. But you can actually derive this from what we already know, and just using some basic logic about like what time evolution is. So what's time evolution anyway? So you start with some, initial condition, and you evolve it to some other time t. And what do we know? Well, we know that, first of all, and maybe we don't even have to say it's at time t equal to 0, it's really at any time t sub 0, and it could be any time. You evolve it to some other time, later time, right, where, you know, t is like bigger than t naught. Well, we know, first of all, that phi of t naught is equal to 1. And we better hope that once it's evolved that none of our probability has escaped. So you better hope that it evolved to something else whose inner product is also 1. And, you know, you would also hope that there would be some kind of operator, right? So this is in your Hilbert space, right? And you evolve to something in your Hilbert space. So whatever time evolution is, we could imagine it as just some transformation of a state, right? And you would hope that, you know, such a transformation would be linear. If you have a superposition of your Hilbert space vectors, you would hope that, you know, you could evolve each one of those pieces separately. So you would expect then that, you know, quite generally, what's time evolution is you take any initial state, right? And you act with it with some operator that, you know, it might depend on the different times. But in general, you take this guy, you operate it with some operator, and that just gives you back your evolved state. So that's what time evolution should do, but it has to have this condition, right? That the norm is preserved. So who can tell me what we must conclude about this operator U?
Must be unitary.
Yeah.
Yep.
It must be unitary.
The U was not a giveaway at all.
Yeah, well, that's right. That's right. And that actually, believe it or not, that's like, okay, so there's one more, right? And there's this idea of, say you like take your system at time t naught and you evolve it to some other time t, right? Yeah, you go along, you do something to your state, you know, it starts here, you evolve it, you evolve it to some other state. Well, you would hope that if you evolve it into some intermediate time, t1, say, in between these two times, then you would hope that this operator, whatever it does, you would hope that like you can just take your evolution and split it up into pieces. It shouldn't matter that we, you know, start with t naught and then go to some intermediate time t1, right? This is our initial state. And then you could evolve it using, starting now with time t1, right? And evolving it to time t. Hopefully that doesn't do anything. I mean, that it shouldn't matter that we do that, that we introduce some intermediate time. You would hope that this is the same as just evolving it from time t naught up to time total time t. As just the point of logic that right? And then you should also expect that if you don't do anything at all, if you just take it at time t naught and you just don't touch the system at all, you should also hope that you get back out just the original state, right? That, you know, nothing happens if you don't evolve it for any time. So those two things actually lets you construct the following identity that for if you evolve from time t naught to t, and then you evolve from time t back to t naught, that you will have undone all of your evolving, and you should get back out the identity that nothing's happened. So it's kind of a combination of these two things that lets you conclude. It's a very logical kind of thing. You say, oh, I'm evolving from t naught to t. And then you're gonna do a backwards evolution from t to t naught. And that's as if I didn't do anything, as if I just evolved from time t naught to time t naught. And I should hope that doesn't do anything to your state. And so, you know, that's a logical kind of thing. And we know, since you mentioned it's unitary, u dagger u is equal to the identity. You can conclude from that that u dagger of t naught going to t is just the time reversed evolution t naught, right? So that's if you combine it with unitarity. And so that's where I leave off. And you can actually use this identity to like show that the Schrodinger equation must be satisfied. You know, from just pure logic, you can like derive the Schrodinger equation. We'll see how that comes in next time, I guess.